This is Geometry, Chapter 8. We're on Lesson 4 on page 319. All right, so we've talked about transformations. And we've talked about congruence when there is an isometry in the transformation, when the transformation is isometric. And the only transformation where there is not congruence or an isometry, which are really saying the same thing, right, is when we have a dilation. Remember, dilations can be bigger or smaller. All right, now we're going to tie the concepts of transformations and symmetry together. So symmetry, there are different types of symmetry, just like there are different types of transformations, right? So something can be symmetrical if, say, I can rotate it and it looks the exact same, all right? So let's look at some cards that I have. Like take this 2 of hearts. The 2 of hearts here, if I rotate it, it looks, if I rotate it 180 degrees, it looks exactly the same, right? The 2 is here, the heart is up. Let me rotate it back. The 2 is here, the heart is up. A heart's right side up, upside down, rotate 180 degrees, right side up, upside down. All right, so there is symmetry in transformations when you perform that transformation and the images look exactly the same. And the point of the rotation or the line is on the image. Okay, so look, this is a rotation. From here, you can hardly see that, huh? Let's do this. That is better. From here to here is a rotation. But that's not rotation symmetry. In order to have rotation symmetry, the center of rotation has to be on the object in the middle of the object, right? The point of rotation or the line lies on the object. So rotation can be like this and it have nothing to do with symmetry. Rotation symmetry is when I pick a point on an object, and I will pick a point and mark it. Let's say that black dot is my center of rotation, and when I rotate it about the center any degrees, the image looks exactly the same. All right? So now, this is a regular triangle. It is both equilateral and equiangular. It has rotation symmetry as well. So the point of rotation would lie on the object, actually at the center. It's at the centroid, which we will discuss that in the future chapter. It's the very center of the triangle. I can rotate it here, the image. I can rotate it here, and it looks exactly the same. I can rotate it here, and it looks exactly the same. So how many times could I rotate it and the image looked the exact same? 3. Whereas the card, I only rotated that once, right? Here I rotated actually twice. Huh? I said 3. There's one image. There's 2 images. There's 3 images. So there's actually 3 images. With this, I have 1 image. I have 2 images, right? Two images that look exactly the same. When you count the number of images that you can rotate it about and it looks exactly the same, that gives you what's called, this is a new word, in-fold, in being the number of images that look exactly the same, in-fold rotation symmetry. All right, so back to the card. How many images look the same? This one, that's one. That's two. So it has two-fold rotation symmetry. All right, the equilateral triangle. How many images do we have? 1, 2, 3. It has three-fold rotation symmetry. All right, so the card was two-fold. The equilateral triangle was three-fold rotation symmetry. Once we know what the number is of how many exact images we have, then we can know the degree through which we're rotating it. So think of a circle all the way around, right? So let's make this go all the way around. There's one, there's two, we're all the way around. All the way around the circle is how many degrees? 360 degrees. So you take the 360 degrees, divide it by the n, the number of exact images you have through the rotation, and you can get the degree or the magnitude of the rotation. So for the card, it would be 360 divided by 2, which is 180 degrees. So that's the magnitude or the degree of the rotation. I rotate it 180 degrees to get the same image, another 180 degrees, and I get the same image. With the equilateral triangle, what is the degree rotation? Well, I take the 360 all the way around and divide it by 3. So its rotation is through 120 degrees. All right, so look, there's one, there's 120, right? There's 240, and then 360 to get back to the original. All right, so I'm going to ask you, do these other cards have rotational symmetry, and what would be the point of rotation? All right, does the Jack have rotational symmetry? What do you think? Yes, the Jack has rotation symmetry. It's twofold. It's 180 degrees. All right. What about the Nine of Clubs? Does the Nine of Clubs have rotational symmetry? Okay, I want you to look closely at it. I'm going to rotate it. Look closely. Are you looking? Okay, I'm going to rotate it 180 degrees. Does it look the same? Here. Are you looking closely? Here. As opposed to here. No, it does not. This image, when I rotate it 180 degrees, is upside down. It does not have rotational symmetry. All right, the 4. Does it have rotational symmetry? Yes, it does. What about the 7? It does not, right? 7 does not have rotational symmetry. Look at the plate on page 319. First, I want you to count. How many horses do you think are on that plate? A lot of them share the same body. All right, so I'm going to give you about 30 seconds to count the horses. Okay, how many horses do you think? Well, with every head, there are 3 back sides, right? So how many heads are there? 1, 2, 3, 4. 4 times 3 is 12. There are 12 horses. Now, just looking at the inside image, not the imperfections on the outside of that plate. Look how they have rotated it. And they have, and those horses look exactly the same through a 90-degree rotation. And so what's the end-fold rotation? Since there are 4 images, it's 4-fold rotation. How did we get the 90 degrees? We take 360 divided by 4, which is 90. Okay, so rotation symmetry. An image has rotation symmetry if with respect to a point that lies on the image, you can rotate it, the image, through an angle of less than 360 degrees. And the image is congruent to the original. All right, that's rotation symmetry. You have to be able to rotate an object through a less than 360 degrees, and the resultant image looks the exact same as the original. All right, so rotation symmetry. Think about items that have rotation symmetry. Squares have rotation symmetry. Equilateral triangles have rotation symmetry. What else? What about a parallelogram? All parallelograms have rotation symmetry. Right, there are a lot of images that have rotation symmetry. I think of looking through a kaleidoscope. Oftentimes when you're looking through a kaleidoscope, there's typically more than 4-fold rotation symmetry. But let's just suppose, okay, I'm making the image as simple as I can. With a kaleidoscope, typically your image is just reflected. So in art class, you often use this concept, rotation symmetry, to draw things. And that's the way the kaleidoscope works as well. This image rotated 90 degrees looks the same. Oftentimes it has less of a rotation. The degree is less because there are more images. And as you rotate that kaleidoscope, the image changes, but it's all done with mirrors, such that this is reflected here, is reflected here, is reflected in each place, all right? So that is reflection symmetry. So point symmetry. What is point symmetry? I'm in the, like, on the top of page 312. An image has point symmetry if it has two-fold rotation symmetry. So point symmetry is true of every object that has two-fold rotation symmetry. If it looks exactly the same turned upside down. So, like, back to the cards. This has point symmetry, right? This has point symmetry. So that's point symmetry. You got it? Point symmetry, two-fold rotation, rotation symmetry through any angle less than 360. The image looks exactly the same. Now, what about line symmetry? We typically call it line symmetry. Your textbook also calls it reflection symmetry. All right, so when do we have line symmetry? All right, this is an isosceles triangle. The measure of this equals the measure of that, and not the base. So we have an isosceles triangle. Two sides of this triangle are congruent, right? The other one is not. Line symmetry says that there's a line that can be drawn through the image such that the left side is a mirror image of the right. And if I fold it in half, you'll see that the images are exactly the same. So line symmetry says, literally, this side is a reflection of that side. We will have line symmetry in Algebra 2 when we get to parabolas. A parabola graphed looks like this. It's a second degree equation. So x is raised to the second degree. And there's a line of symmetry at the what's called the vertex. Typically, you're accustomed to hearing the word vertex with sharp corners. But in math, in your higher level maths, a vertex can be a point at which a curve changes directions. So if the vertex of this parabola, I'll write the word parabola, which is a second degree equation, is at this point, what happens is this curve is decreasing until it reaches the vertex, and then it begins rising or increasing. All parabolas have line symmetry such that if I drew a line of symmetry through the vertex, my line's not exactly linear, is it? All right, the distance from any point on that line of symmetry to the curve is the exact same distance from that line of symmetry to the other side of the curve, so that those would be congruent. And if I folded the curve right on that line of symmetry at that vertex, then these stems, these curves, they're not lines, the curves would actually lie one on top of the other. So line symmetry is important in your higher level mathematics. All right, so this line is called a line of symmetry, this line. In Algebra 2, we're going to call this the axis of symmetry. think XY axis. It's just a line, right? It's the axis through which the left side is an exact reflection of the right. It's like the mirror. All right? So we have rotation symmetry. We have line symmetry. And we have translation symmetry. All right? Translation symmetry happens when we have an isometry and an object is translated, right? So literally if I have this object and I move it and I keep translating it through parallel lines, then that is translation symmetry. Remember, symmetry means very similar to an isometry, except that it means same measurement, right? That's the root of the word, same measurement. All right, so look at what appears to be Egyptians to me on page 320. It's probably not Egyptians, it's just people. But from the original image, who's the guy in red, outlined in red, the next one, all of those are translation symmetries, all right? In symmetric figures, we know that when we have symmetry, we know that the original image is equal to the original image. The original image is equal to its translated image or its rotated image, right? All right. So look at your definition on the bottom, page 320. A pattern has translation symmetry if and only if it coincides with the translation image. It means we're just moving it through parallel lines, right? This is not two reflections like in lessons 2 and 3. This is literally just a transformation. We're moving it left, right, up, or down, all right? Okay, I would like for you to look on page 321 and work problems 1 through 10.